So today's lesson is actually a little bit longer. We're going to continue with section 11.2. We did all the graphing, but we didn't do any word problems, and that's where that applies. So we're going to continue with that, and that kind of ties into section 11.3 using the number E. That's the letter E. So a little bit before we get started with that is, what exactly is that? So the number E, I refer to it as Euler's number, and they use that little kind of like a cursive symbol E. And what you need to know about it is that it is created and defined using this series. That's only the idea behind it. And they use it in different types of equations. So refer to it as Euler's number. It is not a variable, it is a number. And if you take the sum of this series right here, it turns out to be an approximate number, approximately equal to about 2.7. Now, if you have your cell phone and you're doing math with your cell phone, it's going to be, let's see if I can switch this. Okay. So it's that number right there, it's E. So E to the first power, well, if I push an E, it's there. If I were to do like E to the first power, it's there. E to the second power. So if you have to raise your exponent, you're probably going to be using that function. So for example, E cubed, you put the 3 first, and then you hit E to the x, and you get that. If you have your calculator, you kind of have to find where that's going to be. So let's see, on this one, oh, and excuse my cut, it's actually using a shovel and got a cut. Okay, so on this one, it is right here. So it's the second function, it's E to the x. So I'm going to do second E to the x, and it comes up right there. So now I can put in, E to the first power, do that again, second E to the x, E to the second power, or whatever you're going to plug into there, okay? All right, and so that's how you use it. All right, so back to our notes, a little thing about this, so go ahead and copy this down. Before we go to writing our notes, I actually wanted to show you one thing. We know that E is approximately 2.718. So if we did Y equals, and again, you're just watching, don't write any of this down, 2 to the x power, we know it looks something like this. If we did Y equals E to the x, where is E on here? You're actually just going to use the letter E, and it defines it. It actually already knows it's 2.7. Okay, so Y equals E to the x power. Okay, so we can see that this is actually a little bit steeper. I'm going to do one more. Y equals, because it's about 2.7, 3 to the x power. Okay. So you can see I always say it's like Y equals 2 to the x, but because it's 2.7, it's actually going to be a little bit closer to 3 to the x. Let's see what else. Same thing. If you were to graph this one and you did a -5, well, what's a -5 going to do to your graph? Oh yeah, it does the same thing. It's going to have an asymptote at -5, and it shifted it down 5. Something like that. If you put it in here with the exponent, I think I have to use parentheses. Let's do a +4. What's that +4 going to do to your graph? Yeah, it's going to take it and move. Normally it had been, make it a 1 scale. Normally it was here, so it's going to shift it left 4 units. 1, 2, 3, 4. and down 5. 1, 2, 3, 4, 5 right there. And your asymptote is still at -5. So it actually shifts in the same way as any exponential function. Okay? All right. Back to the number e. Now you're writing this down. Okay, so make a quick graph. So we know y equals 2 to the x looks something like this. Y equals e to the x is going to be a little bit steeper. I learned it as Euler's number from Leonard Euler, the Swiss mathematician. So we'll just refer to it as that. It is the number e, and it's approximately 2.7. Okay? Now we're going to use these in different equations. All right, so as a reminder, e is not a variable. It is a number, 2.7. Again, what's another famous number that we know? Yeah, when we think of pi, we know pi is about 3.14. So same, it's not a variable. It does represent a number. We have 3 different equations, and I'll also write the page numbers so that you know where to find them in your textbook. First, we have growth or decay. And the growth or decay, if something was increasing at a rate of 8%, this would be 1 plus 8% as a decimal, so 1.08. If you were losing value, like something is depreciating or losing value at a rate of 8%, well then this would be 1 minus 0.08, again your percent as a decimal, so it would turn out to be 0.92. So this number here could actually be like a 1.5 or a 0.95. If it's more than 1, that means it's exponential growth. If it's less than 1, it's exponential decay. Compounding interest means that it is not just given interest at one time, it's compounded over, maybe it's monthly, weekly, semi-annually, and we'll talk about that. Continuously compounded, this is actually section 11.3 where they're using this base number e, and this is more occurring. Your book uses it in finance. It actually doesn't really occur in finance. It actually occurs more in nature, and I'll talk about that a little bit down in a minute. So go ahead, copy this down, and I'm going to go ahead and tell you what all of these variables stand for, because you might have seen them differently previously. Like for example, this one, you could have seen it before in another math class as a equals your principal amount 1 plus your common rate times the time. So that's your final amount. This is your principal amount, or they use your 0 to represent the amount at initial time. Anyways, copy that down, and I'm going to go ahead and label them as well. So I have the first ones labeled. This is on page 706, 707. This is section 11.2. This is section 11.3, page 713. So again, this is a real typical one, and we're going to go ahead and label these as well. But your final amount, so what you end up with, your initial amount, your rate of growth or decay, and they say per time period, because if this is, it's growing at 3% monthly, and it's for 1 year, then you would have to put in the number 12 here, because this is monthly, and this would be 12 months. Now, if this is the rate 8% per year, and it was for 1 year, then you would plug in 1 year here. So these units kind of have to match. Whether if this is weekly, then this has to be in weeks. If this is monthly, this has to be in months. If it's in years, this is in years. And usually it's in years. Let me go ahead and label the rest of these. So I did the one for compound interest. Again, this is your final amount. This is your principal amount. Here you have 2 n's. It represents the same thing. N stands for the number of times compounded. So if it's monthly, it's 12 times a year. If it's semi-annually, that's 2 times a year. If it's quarterly, that's 4 times a year. R is still going to be your interest rate, and you're going to write it as a decimal. And here is T stands for the number of years. Continuously compounded, same thing, final amount, initial amount. E is not a variable, E is 2.7, or you can just use that button in your calculator. Interest rate as a decimal, and then the time. All right, now we have all the formulas. Now we're actually going to do some work and do a little bit of the problems. So our first problem is, and I write this down in case you need to refer to it later. On page 707, example 3, it says, refer to the application at the beginning of the lesson. Suppose that a researcher estimates that the initial population of varroa in a colony is 500. They are increasing at a rate of 14% per week. What is the expected population in 22 weeks? All right, important information. I need to know my initial population is 500. It's increasing at a rate of 14%. And I should write that it's increasing because it could be decreasing. And I want to know what the population is in 22 weeks. So I go back to my formula and I say, okay, which formula is it? They didn't say anything about continuously growing. They didn't say anything about compounded. They would have to say, oh, it's compounding monthly, semi-annually. So this is going to be our first formula. It's either growth or decay. It doesn't really matter. It's the same formula. I'm going to go ahead and write that down and then plug in all the relevant information. So n equals n initial. So from here, what do I know? Okay, I know my initial population is 500. And it's 1 plus my interest, or it's increasing at a rate of 14%. 14% as a decimal is 0.14. And I want to know the amount in 22 weeks. Make sure that you actually know how to plug this into your calculator. As the problems get more difficult, they're usually solving for that final amount, but occasionally, sometimes they do problems where like savings. Oh, if I want to, save, $50,000 for 10 years at an interest rate, how much do I need to, start off with now? So it could also work backwards as well. Or how long do I need to put it in, so you can solve for different things. Plug this into your calculator. If you're doing your cell phone, you always do order of operations. So it's parentheses, exponents, and then multiply. Sometimes students do 500 times this and then raise it to the 22nd power. That would be wrong. You would have to do parentheses, exponents, and then multiply. All right. So go ahead and plug that into your calculator. See if you have a final answer. So if you plug it into your calculator, I do parentheses first, raise it to the 22nd power, and then multiply it times 500. So you can see my answer. If you have the nice calculator, you don't do it in pieces. You could just plug it all in. So 500 times 1.14 raised to the 22nd power, and you get this. Now remember, wordy problems have wordy answers. So in this case, the question says, what is the expected population in 22 weeks? Well, this was my numerical answer. So what would your expected population be? Well, it could actually be 8,931 or 8,930. In this case, you didn't have enough to make it 31, but you could have rounded it to the 30 or to the 31. So again, you would have about 8,930 varroa in the colony after a time period of 22 weeks or something like that. Okay, so wordy problems have wordy answers. And I'll round down, they round it up. Okay. Okay, so our next example is on page 707, and it's example 4, and it says, determine the amount of money in a money market account providing an annual rate of 5% compounded daily if Marcus invests $2,000 and left the money in the account for 7 years. Go back to my formula page and I say, okay, is this going to be growth or decay? Is this going to be compounded or is this going to be continuous? Well, it's definitely compounded interest because it's telling you. It actually will say the word compounded. If it says compounded continuously, then you would use this one. But if it just says compounded, it's that. So I'm going to write that information down, plug it in. Okay, so there's my equation or formula. And the question was, determine the amount of money in the market account. All right, so plug in all the correct information. Principal amount is $2,000. So this is going to be $2,000. 1 plus my interest rate. Interest rate is 5%. 5% as a decimal is 0.05. Compounded daily. So if it's compounded daily, what number am I going to put that in there? 365. Okay. Number of times compounded. So that's the same thing. So 365 for how long? Times 7. And again, you can do this in pieces or plug it all straight into your calculator. Now this might sound simple to plug it in, but these numbers can be a little bit weird. So if you plug it in pieces, you get 365 times 7 is 2,555. This divided by 365 gives you 1.3 times e to the negative 4. So it's a really small number. Instead of rounding, I'm going to keep it in my calculator, add 1 to it, and leave it this way. So now I'm going to take this answer right here, raise it to the exponent, and then multiply that times 2,000. And that's going to be the easiest way for you to do it in pieces. Now, if you typed it all in together, let me show you what that looks like. So I took a minute, typed all that in. And if you have the nice graphing calculator, it's exactly how you write it here in the formula. If you don't have a graphing calculator, then you're going to be doing it in pieces. So in pieces, be real careful. You would do this part first, all your parentheses, and then raise it to that power. So you could do 0.05 divided by 365, add 1 to it, get your answer, raise it to, if you didn't know, 365 times 7, whatever that is. And then after you have all of that simplified first, remember parentheses, exponents, then multiply it to your final answer. All right, and that's how you would do it, like if you were using your cell phone as a calculator. All right, one more problem. Oh, Becca, can you answer it? It's Dad. Hurry, hurry.
Hello? Yeah.
Oh. Hello? Oh. Yeah, well, isn't it under the keyboard? Oh, shoot. Yeah, I don't know. Maybe when I cleaned, I dropped it or something. Um, okay, bye. Okay, and also wordy problems have wordy answers. All right, and yes, this is a long lesson. All right, here we go in our last example. So our last example says, right here, it says compare the balance after 25 years of a $10,000 investment earning a 6 3/4% interest rate compounded continuously. And then you're going to look at it and also compare it compounded semi-annually. Now, here you go. Now you have to think about this. If you have something compounded continuously over and over and over versus something compounded semi-annually. So semi-annually is going to be how many times a year? Twice. So if you had something compounded maybe monthly or daily or continuously compounded, so what does that actually look like? And which answer should be more? Like how would you want your money invested? Compounded semi-annually or compounded continuously? Now in real life, this doesn't actually apply to finances. It applies more to things naturally occurring in nature, like growth rates, population rates, different things like that, but not necessarily in finances. Your book uses it in finances, so theoretically it has the same idea. But again, let's just plug in these numbers and see what we get. All right, so I'm going to plug this in a little bit slow. You should be trying to work faster than me. So my principal balance is $10,000. E is the number E, not a variable. My interest rate is 6 3/4, so that's the same as 0.0675 for 25 years. Plugging this into my calculator. Again, I can plug it in all at the same time. And if I do it all at the same time, I should get 10,000. You see that? Again, you should be working faster than me. 10,000 E I get about 54,059. Okay. Now, if I did it in pieces or on your cell phone, I'm going to do 0.0675 times 25. I'm going to raise e to that power and type it in 1.6875. Here, I just copied that one. Get that, and then I'm going to multiply it to 10,000. If you're getting a different answer compared to that and you're rounding, you might have a rounding error. So just be careful with that. All right. And so again, easiest way is if you have the calculator. You could also plug this in into Desmos and you would still get the same thing. Let me see if I can pull that up. All right, so I was actually able to pull it up on Desmos. Now remember, Desmos is actually a calculator, also a graphing program. So I just typed it in exactly 1000 E. That's just going to be the number or the letter E on here. And then raise that to the exponent. You have to put parentheses in order to make sure that it all stays in the exponent. And again, I got the same answer. So you can just use Desmos as a calculator as well. All right, so write our final answer. It is 54,000. All right, so now let's compare this one, compounded semi-annually. So semi-annually is how many times? That's going to be twice a year. So we're going to start with the same amount. Our principal amount, 10,000. 1 plus 0.0675. Semi-annually is twice a year. So that's twice. Number of years was 25. So some of you already know that that's 50. What the formula does is they actually try to make you think less and say, oh, number of times times 25. So that's going to be, you know, just 50 times. But if you already know that number, you could just put how many times it gets compounded or just use the formula. Okay, that's it. Plug it all into your calculator. Let's see if I get the same exact thing. All right, so I plug this in and I got just straight exactly because I did my calculator this way. The biggest thing that students miss on this part is just plugging it into their calculator or their cell phone correctly. So if you're doing it in pieces, just be careful. So I'm going to walk you how I would do that in pieces. I would do this division first, 0.0675 divided by 2. Add 1. If you already got the answer, you can pause the video, you're done. But if you're having trouble entering it into your calculator, continue on. So let me do that again. So first do this part, 0.0675 divided by 2. Add 1 to it. So now in here you have 1.03. Keep that number. Don't round it. Just leave it in there. Raise it to the, well, you know, that's 50. So I have that. And then the last thing I'm going to do is multiply it by that 10,000. All right, 52, and I got the same. Now, if I was doing this on my cell phone, and again, if you're done, you can already, pause the video, but if you're having trouble entering it on, or if you're using your cell phone as a calculator, let me see if I can figure this out. So if I was using my calculator, I would probably clean this up a little bit, and I would say, okay, that's 50, just to know that. And then I would also say that, I don't know if I would do that one. Let's see. So do this one, and I'm not a good cell phone person, so. Okay, so I have that part. I'm going to add 1 to it and hit equal after each part. I'm going to raise it. And to raise it, is it this one? I think you have to do the exponent first. Let me write this down. To the equals, and then, oh yeah, that works. Then multiply it by that. Okay, that works. Again, just be careful when you're typing everything in. Otherwise, I would write it down in pieces and kind of keep all the decimals. All right, homework is not too bad, but again, make sure you have the right formulas and you know how to apply them. Also, this one is commonly referred to as the PERT equation because it spells PERT, but that's continuously compounded. Okay, that's it.